All right, so what we're going to do is kind of discuss a few things. This first unit is a lot about functions, function identification, and we'll learn new ways to define and identify functions and some interesting properties about them. So you've already talked in Algebra 2 and Algebra 1 in prior math classes about what it means for something to be a function. So what we're going to do first, before we really get to any kind of formal definition, is we're going to have you with your table groups just come up with some sort of definition for a function. And let's see if you and your group can kind of agree upon one best way to represent or to define a function. So this is a good time to pause and have your table work together, define it, and then I'm going to put up some common things that we hear in class and discuss those a little bit. Okay, so hopefully you're unpaused now. You've had a chance to talk with your groups about what does it mean to be a function. And the things that we typically hear when we ask this question are like a restatement of the same thing. So some people say something as simple as like each x should have only one y, or no repeating x values, or each input has only one output. Or some people talk about it graphically and say, oh, it's something that passes the vertical line test. So we really want to start thinking more precisely about this as we continue with our unit here. But just basically, we want to remember that it's this idea that we have a relation, we have an input and an output. So that's really a key here, is that we have an input and an output. And that input and output is connected in such a way that each input goes with only one output. So you can say that any way you want. You can put whatever makes sense to you. But the idea is that we have inputs that have only unique outputs. So sometimes the best way to define something is to provide a counter example. So if you had some sort of function or a relation rather, where you had an input like the number 1 as an x value, and if that 1 was paired with 4 and with 10, then 1 is paired with more than one output and it's not a function. Seems pretty simple. You guys know it pretty well from your Algebra 2 days. But what we're going to do now is just talk about how would we decide and justify if a certain expression or representation is a function. So what I want y'all to do is kind of go through this one problem at a time. So this first one here says y equals negative x squared. And so decide in your groups which of the relations listed below are examples of functions and justify your answers. So please don't just simply write yes or no. You want to justify your answer here. So this is a good time to pause, talk it over with your table. It's okay to be sort of like questioning and maybe even a little contrary if you're not sure. It's good to test each other's opinions. So see what you think and then come join me again. Okay, welcome back after talking with your group. Hopefully you decided that this is a function. That's the easy part. So we'd say yes, it's a function. Now, I think most people coming off of Algebra 2 would think about that graphically. A lot of people picture what that looks like and they say, you know what, that is a parabola. We've got x squared. The negative sign means it opens down. So if we were just trying to picture that, something like this. And I know from my vertical line test that it passes the vertical line test, and that means that it's a function. It doesn't have any repeating x values. If we want to get a little more mathematical, what we might want to do is try and plug in an x value and see if we get something unique for our y value. So I'm going to plug in 1. So if I substitute 1 in for that x, I get negative parentheses 1 squared. So this is my x, this is my y. If I go to simplify that, I square the 1 first, and then I multiply it by negative 1, so that's just negative 1. Now that's the only possible output if I plug in 1 to this function. So that proves mathematically what we were looking at graphically. So yes, and we can say our justification justification is either this graph or a table where we plugged in a value and proved that we can only get one unique output. All right, let's try that next one. We've got a lovely table there, so take a second and write it down, and then discuss with your table, function or not, why or why not. All right, if you're just coming back, this one, if we want to take a look at it, most people say, hey, you know what? I know what to do with the table. I'm just going to look at the X's on the left, and I'm checking for any repeats. So if you don't see any repeats on the X's, then that means none of those X values is paired with more than one Y value. So we would say, yeah, absolutely, that's a function. We don't have any repeating X values. So sometimes our justifications can be words because there's not really much to draw or any math to do here. On the prior one, our graph or that table were helpful and informative. All right, a new one, we got coordinate pairs, which are honestly just kind of tables in a different form. So take a look at that with your table, decide, is it a function, is it not, and then come on back. All right, so if we look at this, we've got coordinates and the X's are listed first. So when I see this 5 and this 5 here, now I don't want to just assume that because they're both 5 that that is a repeating X. We have to see that indeed it's actually paired with a different Y value in each of those. So the first one is paired with a 6. The second one is paired with a 1. So since those are not, or since those are two unique Y values, or two different Y values, then we would say that this is not a function because 5, let's clean that up, because 5 is paired with two different outputs. All right, and you could have said this a different way. As long as your justification is true and makes sense to you, that's good. All right, we have a couple more. So we've seen an equation, a table, coordinate pairs. We have a new representation. We have something that's already graphed here. So make yourself a quick informal sketch and then discuss with your table, function or not, and come up with your justification. And then come back and join me in just a second. Okay. So if we're looking at this, the one thing that I would encourage you not to rely on and that UT will never speak of is this thing called a vertical line test. The vertical line test that we've talked about for all these years in Algebra 2 is basically a hack. It's a way to understand if we have a repeating X value. So when I look at this, if I look at any point on this sideways parabola, if I have a point that's directly above another one, essentially in a vertical line, then what that means is this input of 3 is paired with two different outputs. And that means no, it's not a function. And then that's going to be the same as that prior one. Same as number 3. All right, we have a number, any input here on the right side of 0 is paired with more than one output, right? So we don't want to say fails the vertical line test. We want to say something like each input does not have a unique output, or a given input is paired with more than one output, however you want to say it. Okay, this next one gets real interesting. They take a nice little jump here. So now we're going to an equation, and it's like that first one we looked at, except it's kind of more complicated. We've got higher powers and things like that. So I would encourage you to think about this, and I don't expect you to know what the graph looks like. You could check out Desmos, but I want you to think about the algebra first. So pause here with your table and think like we did on number 1 about how we did this algebraically to understand, and see if you can decide if this is a function or not. Okay, so if you're coming back, this one is always tricky to people. And if you said this is not a function, you're right, and that's great. But if you don't know why, then that's not so helpful. So this one is not a function. And let's try like we did algebraically on number 1. So let's just plug in 1 for x. And let's see what happens when we solve for y or calculate y. So if I plug in 1 for x to this equation right here, I get 8 times 1 squared. So y equals 8 times 1 squared when I plug in 1. Oh, I got ahead of myself. I don't want to write this part here. So what we've got over here is I rewrote the equation y to the 4th equals 8 times 1 squared. Right? So I just took this equation, rewrote it, plugged in 1. So when I go to solve it, y to the 4th equals, and then 1 squared is just 1, and then that's 8. If I want to solve this to get rid of that power of 4, we're going to take the 4th root. Now, that's not a nice number, but we know, or we should know, when we take even roots of numbers, like square roots or 4th roots, we get a positive and a negative answer. So taking that 4th root means y equals plus or minus, and then the 4th root of 8, don't care right now, it's just some decimal. But here's the key. It equals the positive 4th root of 8 when I plug in 1, but I can also get the negative 4th root of 8. So if I think about it in those terms, this is absolutely not a function. I can plug in 1, and I can get out 2 different y values. Okay, so algebraically, we can see that by plugging in and then solving for y, that we got 2 different y values. So we could say x values repeat. If you were to graph this on Desmos, you'd see something pretty cool looking. It kind of looks like 2 sideways parabolas opening from the origin in opposite directions. So that kind of shows you visually that yes, it's not a function. So if you want, take a second, pause, check it out on Desmos. It's an interesting looking graph. All right, let's try the next one. Here we've got a mapping, if you remember what those are. Now in this scenario, they've labeled x and y, our inputs and outputs. And then as you look at it, all you're going to do is check that mapping and see if you think that's a function or not and why not. So pause and discuss and come up with your justification. Okay, so if we're coming back, we want to take a look, and remember the idea is we can't have an input paired with more than one output. And so right away I can see based on this input and this input, each of them are paired with more than one output. So we'd say no. An input is paired with more than one output. All right, that one's pretty easy. I mean, you really just look to see if the input is going towards more than one output. All right, last one, and this one is sort of real world, not so much equations or anything anymore. And I think typically people think of this as like we've got names on the left and then colors on the right. I'm going to let you guys decide what that means. So talk it over with your table. Do you think this is a function or not? Okay, so sometimes this gets some interesting debate, but most people generally see the names as inputs. So like Tom, Jill, Bill, and Harry. Those are my elements in my domain. Those are the inputs. And then blue, brown, green, and green, most people assume these are eye color. So if we're treating it like that situation, and we think of this as a mapping, all we're looking to make sure is that Tom doesn't have more than one eye color associated to him. So Tom is only with blue. He's not also with brown. Jill is only with brown. Bill is only with green. Harry is only with green. So it's okay that Bill and Harry are both only with green. If you wanted to think of this as a mapping, sometimes the mapping helps. So Tom, Jill, Bill, Harry. And then we've got blue, brown, green. So Tom is blue, Jill is brown, Bill is green, Harry's green. And that mapping, it's okay that the inputs both go to the same output. That's a function. The other way around doesn't work. So yes, it is. All right, first exploration. Check it off. Go ahead and start that Delta Math.